Sorry, I guess sorry. Yeah, thank you for all the great presentations. My first question is for Lingzi. So it's interesting the Gersite distribution you are trying to locate and trying to pinpoint. I wonder how that relates to hematite finding on the moon. The reason I'm asking is if we do have Gersite, if there were impact gardening, do you expect any correlation between that and the hematite finding on the moon? This is left field question. So, yeah, thank you.
Yeah. So Schweiz's hematite distribution is basically the same pattern, concentrating toward the polar region and the near side of the moon. So they're definitely correlated. And Schweiz's theory was hematite was dehydrated goethite.
Oh,
so
okay.
they're definitely correlated.
Thanks.
Hi, Paul Lucy, Marriott Hotels. Ed, the great work, really interesting. I just wanted to mention that you know, the PSRs in general are unique, but different from the background in both the Lyman alpha and at the laser wavelength, and those they kind of shied away from the ice explanation, more sort of differences in physical processes. So, could the physical state, constant low temperatures, be affecting, say, gardening or something to cause this radar distinction between the PSRs in the background?
Yeah, so although the PSRs look different for other wavelengths, we have not seen a difference in their radar properties. And one of the reasons that I am cautious to saying, hey, I found a signature of water ice, is we need to do a little bit more analysis to actually be able to untangle the effect, because dielectric permittivity can be changed because it has water ice, or it could be changed because it's fluffy or regolith, or less fluffy regolith. So we need to do a little bit more. That way I could actually tell you yes, water ice or no. Yeah, thanks for the question.
Hi, I'm Sarah from Georgia Tech. I had a question for Carl. Charles, sorry.
Carl, yeah.
So were there any measurements taken after the ice deposition for when you had the ice putting? Yeah.
So the way we did the experiments, when it was in the glove box, we would do intimate ice mixed in with the regular, and we'd make the measurements in glove box, went out to 2.5 microns, right? Now, when we did the measurements in the vacuum chamber, we either did the same thing, or we, wetted it and ground it all up. And then when we put it in the vacuum chamber, we found that the surface already desiccated, and so then we lased it to break it apart and got the fresh surface exposed. And then after that, we opened up the chamber and let Maryland air get in to form the frost. So that was procedures. Did that answer your question?
Yeah, that actually did.
Great.
We're going to interrupt the in-room questions for an online question from Janice Bishop. Feel free to unmute, and this is for Ling Zhe.
Hi, Ling Zhe. I was really intrigued by your talk, and I think you've done a great job mapping this intriguing feature at 1.5. However, I don't think this could be goethite because I've studied the spectral properties of iron oxides for over 30 years, and goethite doesn't have a band at 1.5 microns. So I suggest you take a look at the Relab database and look at goethite spectra there. And I don't know why the USGS spectrum of goethite that you showed has a weird band at 1.5, but they have Roger Clark and Greg Swayze published a paper in 1990 where they identified scapolite on Mars, and then they had to retract it because of an admixture, an anomaly in one of their lab spectra. So I would proceed with caution, and I think you've done an excellent job with your study, but I suggest you go back and look more carefully at goethite spectra in the laboratory. And I'm guessing you found some really interesting kind of ice, different from the normal ice, or maybe something else. Minerals don't typically have a band at 1.5. So There are some wacky, weird ones that do. So maybe maybe you found that, or maybe it's some intriguing new kind of ice that is novel and interesting too. So I think it's a great discovery, but I don't think it's goethite. And I want to save you from the mistake that Roger Clark and Greg Swayze made in 1990.
Yeah, thanks for the comment. We found several other literatures that showed goethite have this 1.5 micron absorption, which is the OH. That's a typical OH absorption.
Yeah, OH absorptions usually occur at about 1.41 to 1.45 microns, and in constrained environments, they can have a band up to 1.47, like in academia, but I would be very cautious with this interpretation.
Okay, thank you.
Okay. So my second question is for Anthony. In Su et al. 2025, we looked at the sulfur ingassing into the orange beads. And I think we stopped at, talking too much about the sulfur outgassing and ingassing because of the valence consideration. So I probably missed the point that when you talk about the modeling, like sodium outgassing has to be oxidation or reduction related, and the sulfur is more like oxidation involved. So I was wondering whether it's just my misunderstanding, or you're actually looking at more combined, because we do see both happening in terms of outgassing of both elements, ingassing of both elements. They may be separated somehow. The ingassing thickness is different. In addition to that, when the sodium outgas, they recondense as sulfide. So there is a very complex story here. So I'm just kind of wondering, when you do the modeling, what are you planning to do?
Yeah, so I modeled it as simply loss first to indicate the directions, to indicate that the reverse is the opposite. So I guess what I would say is that the electronic mass balance, if both things are in gassing, the redox state must be changing. It must be. There's no other answer for that. So until that data showed the sulfur in gassing too, I was like, oh, that's curious. If we accept both are in gassing, we must have a redox state change. So yes, it is very complicated, and I think I've settled on what I think is the most. If this is real, this should show up to see if that matters. But in terms of the modeling, I'm not quite sure yet. It may be equilibrating with the plume the entire time, to where that's what it is. But we should talk more about it, because I don't have the right answer completely.
Okay. Yeah. Thank you.
Jeff Gillis Davis from WashU. My questions for Pratik. I was curious, in your model, does viscosity of the melt and the composition of the volatile that forms the bubble play a part in how quickly the bubbles coalesce? And can you infer anything about the composition of the volatile that made the bubble from those modeling? Excellent talk, by the way, too.
Thank you. So I have just shown the equation in the presentation, but we are using a differentiation form of it. And at every step, we are changing the viscosity. We are calculating the viscosity from the liquid temperature to the glass transient temperature. And at each time step, we are integrating the viscosity, how it is changing with time. So yeah, so we are changing the viscosity, and we have seen that beyond 1150 Kelvin and lower, the viscosity becomes too high, for bubbles to coalesce or relax its film. If it's relaxed, it's maybe few microns. Coalescence cannot take place beyond that temperature, because viscosity is becoming too high. When some literature say that at that temperature, olivines also start to crystallize, and that can also increase the viscosity. But regarding the composition of the vesicles, we are not sure what those compositions are, because we don't have the entire glass bead. We just have a cross section of them. So during procedure, they are expected to loss of volatile from the which was trapped within the bead. So I don't have any comments on the composition of the vesicles, but we expect those are mainly sulfur or maybe dissolved H2O, because there are some studies on these orange glass beads to understand the liquid like volatile content from the origin of the melt, and they has like mainly sulfur and H2O or OH.
So you can't simply assume a load or pressure outside the bubble and the composition inside the bubble of a volatile and the expansion rate of the different molecule can give you the size of the bubble for kind of a inside outside pressure.
Okay, I will look into that. Even like we are also like if a bead is cooling in a 1 second, we also expect the bubble might grow in that period of time. So we'll also integrate the bubble growth model into that and see how it is affecting the time scale as well. Thank you.
I'm going to jump in with a question that's in the chat online here. This is from Ardith Bravenik for Lee Ciao. Do you have a sense of the minimum millimeter required to protect the amino acids?
That depends on the duration of irradiation we're talking about. So for the study that we did do, 8 millimeters had a survivability rate of at least 90% for the equivalent of about 2.5 years on the lunar surface. So that's multiple variables happening at once. That gives you a sense of what's needed.
This is Paul Lucy for Carl. So I totally agree. 3 microns is a great place to look for water ice, but a technical challenge is there's not a lot of light at 3 microns in the PSR. It's just the way the sun and thermal interact. But I did want to make the comment that ice has a really strong 12 micron band where there's a lot of light in PSR. It's just a comment and maybe encourage you to take a look at that in the lab, or we could work together on it.
Let's work together on that. My system stops at 8 microns. Okay, sounds great synergy.
Sarah Soul from Georgia Tech. I have a question for Janice for clarification. Unfortunately, 10 minutes is just not enough time to go through as much explanation as you would like, but could you repeat what you mean by you coming up with different forms of hydration?
Sure. What we see is a different shape in the band depth, the band parameter near the hydration band near 2.7 to 3 microns. And for the highlands, we see sort of a plateau or a bowl-shaped change in the water from morning to midday. And for the mare, we see increasing shape. So we see when we're mapping this hydration band across the moon, we see changes in composition and changes with time of day, which has been seen before, but we looked at this more carefully in terms of specific regions of the moon. And now it really seems that there's a persistent hydration band that's present in some materials. And then there's a variable hydration band that's present in other materials. So in the mare, there's this variable component with time of day. And in the highlands, there's a more persistent component that doesn't seem to change or changes less. And so it really looks like there are 2 components. Does that answer the question?
Yes, thank you.
I'll jump in with another question from the chat. So this is from Janice Bishop for Zi Huang. I think your work is very important to understand the M-cube hydration bands. I'm wondering if you have tested different types of mineral structures in your modeling.
Yes, so this is definitely our next step. So we're planning on doing this for olivine and also ilmenite, especially for those complex, and also like for complex mineral structures compositions. So hoping to test, I think there's a recent paper identify like different variation of 3 micron bands depending on different mineral species. So this is what we're planning to do so as well. Thank you.
Hi, this is Paul Saba, UC Berkeley. I also have a question for CU. Maybe I missed it. Is there a big difference whether you have a silicon or an oxygen point defect in the simulation?
Yeah, so there's definitely a very huge difference. Unfortunately, given the time limit, I don't have the time to show all of them. But essentially, like silicon DFAT is going to trap those hydrogen very effectively, and also the oxygen DFAT is going to trap the water more effectively. And also, there's also an interesting deviation for the spectra, given the trapping of water with silicon oxygen DFAT. I'm going to show that in the full paper, so you can check it out.
Thank you.
Lucy, this is for Janice. Janice, I noticed in your diurnal plots that there was pretty weak latitude dependence, but Schweile's maps show a really strong latitude dependence. Can you comment on that?
That could be due to the thermal correction that's used. And Roger Clark came up with an initial one at the time the M-Cube team was working on this, and then that was improved by Schweile and Josh Banfield and also Christian Willer. And then his grad student Kai Wolforth used data from the Galfun mission and from Diviner. And I think his thermal modeling makes the most sense from physics, and it's what's used by the asteroid community and others. So I think Schweile's method is also reasonable, and I don't know why the magnitude is different, but it could be that there's some variations in maybe he's detecting more because of how his thermal modeling is correcting the data. That could be.
Okay.
But I think that the trends are pretty similar to what Schwei's finding and what we're finding. It's just a matter of magnitude. Whereas the early corrections that Roger Clark did were a little bit different character.
Yeah, and Josh Banfield, his correction showed very little latitude dependence too, though he didn't look at the diurnal. So I guess there's still more work on the thermal correction to get a consensus.
Another question from the chat, also for Janice. It is, where do you see an increase in OH and H2O with an increase in pyroxenes and also with lunar diurnal cycle? And how are you considering the thermal emission effect around 3 micron band? And what calibrations are you using?
Okay, I did answer that in the chat, and we're using the thermal calibration from Christian Willer and Kai Wolforth, and they corrected this with the Diviner data as Schweile did, but they also used the Chinese Galfun mission in order to characterize the thermal and ensure that it's consistent with physics. So I think their thermal correction is the most accurate, I believe, based on physical properties and remote sensing of airless bodies. And the pyroxene, I think that's not something new here. Pyroxene's known to be more consistent with the Mare, and we're just kind of pulling this together in this talk. So looking at the lab spectra and looking at the change in shape of the hydration band from morning to midday is what we're looking at here. I don't know if that addresses the question.
This is Caleb Fassif. Maybe I have a question for Pratik. This is probably a little ignorant, but you showed this really interesting trend in the core of the orange glass beads at the top and the black at the bottom. But I guess my question is, like, what fraction of the core is glass beads going from the top to the bottom? Is it like radically reduced as you go from the top to the bottom, or is it sort of a constant amount through the core?
So if I understood correctly, like how much is glass at the top and black at the bottom?
No, you gave the sort of the what the different types of beads were, but how many beads are there at the top and the bottom is the question I have. Is it sort of homogeneous, or is it decreasing with depth? Or
yeah, like more or less, like in the smaller fraction, the amount of glass is much more. Like, but if I go for a pyroclastic bead size for 250 micron and above, black, the crystalline becomes more dominant because there are no glass beyond 500 micron. Like I'm getting black beads, and this is consistent across all the depths. So, but for smaller fraction size, the glass remains around 20 to 30% at the top of the drill core, but at the bottom it's less than 10%.
I have a question for Steve. I think this is a cool idea of using the glass beads as analogs for thinking about impact glasses, and I've just been sitting here sort of pondering how the differences in the initial condition would affect the chemical profiles that might develop. Like the temperatures would be so much higher.
Yeah. So, people have looked at impact glass beads and partly they distinguish them from volcanic beads by the basically absence of water and other vols. So they are highly degassed and the assumption is that they had a much higher temperature origin. And so then, we're thinking of looking at like copper or zinc and see how, and moderately volatile elements that may be preserved even in this high temperature regime, for sure.
Yeah, this is for you. So I'm a little concerned about the net intensity of the infrared absorption imposed by your process. So I guess my question is, for a given hydrogen atom, how long does it persist as in the form of hydroxyl versus not hydroxyl? So just an estimate. You said the bond length, the lifetime of the bond is very short. So if it's usually hydrogen, then the net absorption is going to be fairly low. So, but can you comment on the lifetime as hydroxyl versus lifetime as hydrogen?
Life as hydrogen, you mean atomic hydrogens or?
Well, for a given hydrogen that sometimes is bonded and forms a hydroxyl that's long enough to form an infrared absorption, is it 99% of the time hydrogen and once in a while it's in hydroxyl, or is the hopping so frequent that it persists as hydroxyl for a long fraction of its lifetime before it diffuses out?
See, so yeah, thanks for the question. So essentially, right now, based on our current simulation results, we only see like transit hydroxyl form with different oxygen. So I wouldn't see that as a consistent hydroxyl oxidation because again, the lifetime is now as long as 1 picosecond, which is the lifetime for hydroxyl stretching. So I wouldn't see this as honestly, I don't think this is also like free hydrogen because I would consider free hydrogen as diffusion among the interstitial silica surface and also within the silica. So I would say like right now, we're gonna do more simulations and also identify the lifetime for like individual hydrogens and also the lifetime for this hydroxyl. But right now, at least limited to this defect case, we are seeing like transit hydroxyl and now, and they're like very, very short term, less than 1 picosecond.
Tom Orlando from Georgia Tech. This is for Ardith. The question is related to the. So you showed some really nice glass transitions and phase diagrams, but this is an assumption that these things are in thermodynamic equilibrium. But when you look at the cryovolcanism, there's this very, very fast thermal extraction rate. So it's the cooling rate that really matters. You can get in an argument if you have a really rapid cooling, you're not even thermodynamically coupled through the metal stable state through supercooled water to the glass transition. So there's a lot that has to do with the sort of overall cooling rate. So could you sort of address that as how that would fit into your sort of modeling and your overall picture of these complex solutions?
Yes, thank you so much for the question. I actually had another slide that I entirely deleted that had to do with the critical rate and cooling rates. But I will back up a little bit and say that the reason for this project was that here in Curation, when we were trying to synthesize some icy simulants to do some cryogenic regolith ice testing, one of the problems was that depending on the cooling rate, depending on how we were doing vapor deposition or trying to dose the regolith, we were often observing glasses instead of crystalline ices. So no, the critical cooling rates for many of these in the literature review haven't been reported. There's not a lot of data there at all. I think there needs to be a lot of experimental work to really fill in those gaps because, as you say, that's another entirely important part of this picture. But since we have experimentally observed some of it, I do think that they are going to form glasses.
Yeah. All right. Thank you.
And we hate to cut off the conversations here, but it is 11 o'clock, so the session is officially over. We encourage you to chat with the speakers during the break or email them if you have any more questions. And with that, let's thank the speakers again.